Hello students, welcome to yet another lecture on simulation. Today we are going to discuss simulation of a non-homogeneous Poisson process. In order to motivate the simulation of non-homogeneous Poisson process, let me first go and define what is a Poisson process, what is a non-homogeneous Poisson process. So in order to define a non-homogeneous Poisson process, let us first understand how a non-homogeneous Poisson process can arise out of a homogeneous Poisson process. So here is a setup. So in this setup, what we have said is NT is a Poisson process with rate parameter lambda. It's a homogeneous Poisson process with rate parameter lambda. I have been given a function p, which is defined from 0 infinity, that is set positive part of a real line, to the closed interval 0 1, and it is integrable. So this is the condition given to me. Now what happens? We are trying to understand some process. In that, event takes place with Poisson process with rate lambda. The event occurs with Poisson process with rate lambda at time s. If the event occurs at time s, then it is registered with probability ps, and that probability ps is independent of everything else. And now we are interested in understanding the behavior of new random variable RT, which is the number of events that have been registered in the interval 0 to t. Here is assume that R of 0 is 0, that's why this is 0 is open. Okay. And if it is so, then what actually happens is this RT follows Poisson distribution with rate given by this expression. Okay, and this T evolves over time. So RT is a new kind of process, and marginal distribution of RT is given by the Poisson with rate parameter lambda times integral over 0 to t PSDS. So this is an interesting observation. Let us see how this distribution arises, or let us try to prove this, so that we will have some understanding over the inter-arrival times or event times of a Poisson process. So now assume that let us try to prove this result. So in this for proving this result, let Si as usual be the time of occurrence of ith event. So it is the waiting time that is required for ith event to happen. And now it has been given to you that Nt is equal to m. The moment something is given in the form of Nt is equal to m, we should remember Campbell's theorem. Right? So according to Campbell's theorem, the arrival distributions are nothing but ordered uniform random variables over 0 to t. So order statistics of uniform random variables over 0 to t. Okay. Now let us try to see if Nt is equal to m, what will be the fate of Rt? That means m events have happened up to time t. Out of these m events, how many events have been registered is the question. That is what RT will be. So in order to define RT, you can effectively use, since m events have already happened, I is equal to 1 to m, and S1, S2, Sm are already known to you. Now your job is, if we want to determine what is RT, our job is to see whether the event is registered at time, event that happened at time Si is registered or not. So that job is done by this particular random variable ISI. So RT is nothing but indicator random variable of Si summed over I equal to 1 to m. Now given S1, S2, Sm, because of the assumption, the third assumption in this expression, that is independent of everything else, this happens. I can say that ISIs are independent of S1, S2, Sm. Given S2, Sm, they are independent, and therefore probability of ISI is equal to 1 given SI is equal to S is PS, which because it will be a Bernoulli random variable, as this is indicator random variable. PS will be 1 minus probability of ISI is equal to 0 given SI is equal to S. So I know this distribution. Now RT is actually ISI. I know the S1, S2, SM, the distribution of S1, S2, SM given NT is equal to M is nothing but the distribution of U1, U2 up to UM, where UIs are uniform 0 to T random variables. So now by Campbell, this is by Campbell's theorem. So essentially now RT is summation over ISI, which actually equal to, in the light of Campbell's theorem, which actually equal to this. But since they are ordered, whether I am summing something first or second, it doesn't matter. So essentially this reduces to summation over IUI. Okay, fantastic. That essentially means RT is nothing but summation over I equal to 1 to M, indicator function of UI, and UIs are uniform 0 to T random variables. So now, what is a probability that IUI is equal to 1? We already know UI is a uniform random variable over 0 to T. So the density, it has density PT. And the probability, we have already said that ISI equal to 1 given SI is equal to S is PS. So naturally, this will become PS into the density of uniform, that is 1 by T ds. So the density, the IUI equal to 1, the probability is 1 by T PS. You call this probability as some alpha. So this is some probability alpha. Now you know these are Bernoulli random variables and we are looking at the sum. So probability that RT is equal to K given NT is equal to M will be nothing but probability of summation over I equal to 1 to M, because RT is summation over I equal to 1 to M, IUI is equal to K given NT is equal to M. Now given NT is equal to M, this summation, because IUI themselves are independent, therefore this will follow binomial with parameter M and alpha. This will follow binomial with parameter M and alpha. Therefore, this probability will be given by this expression, that is M choose K alpha raised to K 1 minus alpha raised to M minus K for K equal to 0, 1, 2 up to M. Then we are done. Once we have this, then I just need to sum over all M's. So probability of RT is equal to K. Its summation over M is equal to 0 to infinity. Probability of RT equal to K given NT is equal to M into probability of NT is equal to M, which will give me, after some little bit algebraic manipulation, an expression of this form. This is the form of the expression. And therefore, we can conclude that the distribution of RT is Poisson lambda alpha T, where alpha is 1 by T integral over 0 to T PS ds. Therefore, lambda alpha T is this. Correct? Now comes the interesting point. Now, RT follows Poisson process. RT has a Poisson distribution in the marginal for every T. RT minus RS you consider and you consider RS, both of them are independent. So the increments are independent. But the problem is these increments are not stationary as they specifically depend on this T. So the increments are not stationary and therefore we will identify such processes as non-homogeneous Poisson processes. So I have shown you a methodology through which we can simulate or we can generate a Poisson non-homogeneous Poisson process using a homogeneous Poisson process. So in particular, what is the definition of a non-homogeneous Poisson process? So here is the required definition. Let lambda from 0 infinity to 0 infinity be a given density function, which is integrable over all finite intervals. Then you define capital lambda of t as integral over 0 to t lambda sds. Using this lambda t, we will define a generalized non-homogeneous Poisson process. So here is a definition. A counting process NT is called a non-homogeneous Poisson process with rate function small lambda of t if NT has independent increments and NT follows Poisson big lambda of t for t greater than or equal to 0, and we denote such process as NPP lambda dot. This definition automatically implies that whenever I have Nt plus S minus Ns, I will have the distribution of Nt plus S minus Ns as Poisson lambda t plus S minus lambda S. N of 0 will be 0, and all other properties of homogeneous Poisson process, except for instead of having lambda h, we will have lambda t. All other properties are same. Now, what are the implications of this definition? Earlier, our inter-arrival distributions were independent. Now they no longer be independent. Our waiting time distributions will not be sum of, therefore our waiting time distributions will not be sum of independent random variables. So with these two limitations, we need to simulate a non-homogeneous Poisson process in a successful manner. So let us try to again go back and focus our attention on how to simulate a non-homogeneous Poisson process. So our goal is to simulate a non-homogeneous Poisson process. We have seen the definition of non-homogeneous Poisson process. We have understood how non-homogeneous Poisson process arises out of homogeneous Poisson process. So we will try to use this knowledge for simulating non-homogeneous Poisson process. So as you can see, I want to find a non-homogeneous Poisson process with rate function lambda t. Remember what we have done whenever we were dealing with hazard rate function. We first figured out what is the upper bound of this lambda t. So when lambda t is less than or equal to lambda, we tried to do something. So that same thing we will do. We will first choose lambda such that lambda t is always less than or equal to lambda. Now remember, we are simulating a non-homogeneous Poisson process. So what we are trying to do is, we will try to simulate a homogeneous Poisson process, and the way I derived the previous theorem, I will try to take the events with some probability. So essentially I have chosen one lambda for which lambda t is less than or equal to lambda. Now what I will do is, I will use this lambda and simulate a Poisson process with rate lambda. That is what the next step is. So I have generated pairs of uniform random variable. Ui and xi's are exponential with mean 1 by lambda. Then I have set n to be minimum over n, summation over I equal to 1 to n, xi greater than t, because I will fix the upper bound capital T over the time space. And this means I have simulated a Poisson random variable with mean lambda t. Now I need to simulate the other parameters, the other interarrival distributions. Right? So for capital N is the highest number that I can get. So I need to get 1, 2 and so on up to n minus 1. So what I will do is, I will simulate for j equal to 1 to n. I will set ij is equal to 1 if from the pair ui I got uj is less than or equal to lambda times summation over I equal to 1 to j xi by lambda. Remember, this is our probability. This is what we did for simulating hazard rate function. So now, if this condition is satisfied, I will set ij to be equal to 1. That means at jth event, the event is registered. So I will isolate such a set, that set j such that capital J is equal to small j, such that ij is equal to 1. That means for the all the points in this set j, the events are registered, and these events are event times. So the events are registered and the event times are successively given by summation over I equal to 1 to j xi, j belonging to j. That simulates my Poisson process. That means what I have done is, when j is equal to 1, I have set ij equal to 1. So I will have some k which is less than or equal to n events, and all those events I will assign 1, 2, 3, 4, and so on, depending on this, and how to assign these 1, 2, 3, 4 at these times, at these event times. So this is how we will simulate a Poisson process. Let us take one example. Let us say I start with this. So I have generated a pair of random variable u1 x1. Now I will check whether this x1 is less than or equal to t or not. If it is less than or equal to t, what I will do is I will consider this ui, and I will consider the value of ui and check whether this ui is less than or equal to lambda times x1, lambda of x1 upon lambda. If it is so, I will assign that x1 to be equal, I will assign that j I1 to be equal to 1. If not, let I1 be 0. Right? Next, again I will go to U2 and X2. I will check whether X1 plus X2 is less than or equal to T or not. If so, I will come here. I will take this U2 and I will check whether U2 is less than or equal to lambda times sigma xi by lambda or not. And again I will, if so, I will set I2 is equal to 1. Otherwise, I will set I2 is equal to 0. And again, I will go back. How long I will go back? Till I exceed this T. And whenever I exceed this T, at that point, I will stop. Okay. So this is the algorithm that I will use to simulate a Poisson process. This is a very easy prototype algorithm which was similar to hazard rate function. Only while simulating hazard rate functions, we don't have to consider these things, the set of capital J. We just can simply consider the distribution. So here that this is something extra. So this is sampling of a Poisson process from a homogeneous Poisson process. Now, when we use this algorithm, we need to see what are the advantages and disadvantages of the algorithm. So the first observation is, if this lambda t is very close to lambda, then this algorithm gives very good results. However, because I am dealing with some awkward function lambda t, which is integrable, I may not get a lambda t always close to lambda. In that case, the algorithm suffers from rejection, several rejections. So in order to minimize that, what can we do? So can there be a better algorithm? The answer is yes. What we can do is, wherever there is a lot of variation in lambda t, you can split the intervals. So essentially you can split the interval 0 to t into k disjoint intervals, which are given by ti minus 1 to ti, and union over I equal to 1 to k ti, and this interval will be your 0 to t. So basically this is 0 less than or equal, 0 equal to t naught less than t, t1 less than t2 less than tk equal to capital T. They will form a partition. For each set in the partition, you choose lambda I. Remember, this partition may not be equidistant. It may depend on the variation of lambda t. So in some interval, if lambda t is too much variable, then you can split it into further smaller intervals. So do whatever you want and choose for each interval an upper bound lambda I. Once you do that, you have several upper bounds. So in particular, in this case, we will have k different upper bounds, lambda 1 to lambda k. And for each interval, you need to use an algorithm that is discussed in the last slide, or the previous algorithm. But the modification is, I don't want to lose out on the simulated random variables. So we will try to modify this algorithm suitably. So here is a modified algorithm. So now there are two things. Initially, when we used the first algorithm, we had only one interval. So lambda t was less than or equal to lambda. Now I need to identify, when if I am computing an exponential random variable, which interval that random variable belongs to. That is the main thing. So what I will do is, I will set t is equal to 0. That is, I am starting from the initial point, and let this I be the interval identifier. So I is equal to 1 means, because t is equal to 0, I am in the first interval. So I is equal to 1. In this particular interval, what you will do is, you will generate a random variable x following exponential with mean 1 by lambda 1. In particular, wherever you are, you will always simulate a random variable with exponential with mean 1 by lambda I. That I denotes where you belong to. Right? Naturally, once you simulate, you need to check whether you still belong to that interval or not. So you will check whatever is the t, you add this newly generated x and check whether t plus x is less than ti. If this condition is met, that means you are still in the first interval, and therefore your bound of lambda 1 will work. So, in this case, you set t is equal to t plus x, and then generate a random number u, and check whether u is less than or equal to lambda t by lambda I. If so, you accept that event time. So essentially, in earlier thing, we were setting ij to be equal to 1, but here ij's are not there, so I am saying accept the event time. And then you go return to step 2. Once again you got back to step 2. Now you again generated x following exponential lambda 1 by lambda 1. Now what happens? It may happen that the t plus x may not be less than ti. In that case, you are jumping into the second interval. Suppose it is so that it belongs to the same interval, then again you do the same thing and see whether you are able to accept or not. Right? Suppose it is not less than ti, then you will go to the another step, that is this, and your t plus x is greater than or equal to ti. Now there are two cases. So right now it is I1. So now I will exceed the limit of I1 and I may go to I2. There are two cases. Either I may go to I2, or x generated may be so big that I will exceed everything. Okay. So in that case, we need to be a little more careful. But suppose, let us now, if I is equal to k, then I will stop. Right? Because k means that was the last end point. So I don't want to simulate beyond beyond the end point. Right? If I is not equal to k, then reset, then you reset your x, that the simulated. And remember, what was my x? Let us say x was exponential with mean 1 by lambda 1. And now you have simulated another x. So I want to scale this down. So what I will do is, because it is simulated with mean 1 by lambda 1, I will first multiply that number with lambda I. Also, I have done some transformation like t plus x. So that transformation is there in our t. So what I will do is, from this t I will eliminate ti, which is the endpoint, t minus ti plus x. Now this x was simulated with rate lambda 1. So I will multiply the lambda 1 here and I will divide by lambda 2. Why am I doing so? Because I want to simulate a random variable with mean 1 by lambda 2. Okay. So this x will be exponential with mean 1 by lambda 2. Hmm. And once you have done that, then you reset t is equal to ti and you have gone forward in the interval. So I is equal to I plus 1 and you go to step 3. Step 3 is this. Again you will check t plus x is less than ti. Yes. Then you will set t is equal to t plus x and all those things, because I is I plus 1. So again you will try to see whether you can accept or reject. When the algorithm will terminate? When I is equal to k. The algorithm will terminate. So this is the modified algorithm for our non-homogeneous Poisson process. So effectively this algorithm will work better because it has a finer meshes. Only thing is it will cost some computational efficiency, but the number of rejections will be less if you are fine tuning these lambdas. So the efficiency cost is almost nullified. But if you are very much fine tuned lambdas are there, then this process will yield much better result. This algorithm will yield much better results. That's all for now.